Yeah, don't you forget. Okay, so just to reiterate on tape, the lab that we did yesterday will be due Monday night because we don't have school tomorrow or Friday. Lab yesterday. This lab is historically the longest one of the year. I was optimistic because, well, I thought that in class everything went swimmingly on Monday and that you guys are going to be more on top of this than normal. And you probably were a little bit, but it was still frustrating. And, the goal is not to be frustrating. The goal is for success. And I know we had different kinds of problems with different people. With one group, the resistors were all wrong, which probably meant that the multimeter they used wasn't giving them reliable numbers for the resistance. So we remeasured the resistors, it worked out. With another one, a circuit that I helped them put together, R4 and R5 were swapped. And so their calculations weren't right. Also, the measurements of current weren't right. And so when we did everything, then they matched up. Hopefully you guys saw success. If you have questions, if you need help, even during break, you can still email me. I'll still be available to help you, at least via email. Because the goal of that is for you to be able to see the experimental results match what you get when you apply Kirchhoff's laws. Right. Learning how to do math, if it doesn't give you the right answers, is really not very useful, ultimately. And so I want to make sure people do achieve that goal. Today, we're going to very quickly talk about transient circuits, and that will be the end of material that will be covered on the exam next week.
Do we have a results around It says it does, but I don't understand, so I'm not going to
I'll have to look at that. I'll have to look.
Okay, that's it.
And then we're going to start in on magnetism. And first, I have some woo clap questions for you. It's right?
No.
It's not right?
Nowhere.
Nowhere near? Well, then I'll have to be more careful with my math. Okay, so let's connect on up. We got 2 people connected already. Yay. Now Max has joined us.
That's probably a special thing to create them. Or is this like free?
They're free.
So I could do this different.
Yes, you can. Now, they have additional functions that I don't use that you have to pay for.
I don't like it.
Okay, we got 7. 7 down, 3 to go. Eight, 2 more. Okay, I do need to move on. We can't wait too long. One of the good things about clickers is people are connected quicker. Okay, well, let's go to our first question. Which terminal has a more positive voltage in the figure below? Got 6 in. Anyone else can answer? And we are over 50% participation, but 60% isn't that much higher. Well, I'm going to move on because time. I do encourage you to try to answer these because it helps you to make sure that you have understanding. We got a seventh person.
I forgot to click submit. What's the loop clock code again?
It is, go back, there.
Oh, it's still, no, it's just.
Okay, so the answers we have are 0, 8, 0, 0, with 2 precincts not reporting. We're kind of like a Democratic caucus here. Which terminal has a more positive? Everybody agreed. B is more positive. That, in and of itself, is a big victory. That is often a point of confusion, but it's a simple way of determining, which everyone has figured out, but it's often a point of confusion. So I'm feeling good about you guys right now. Back to feeling good about you.
Oh my.
For 3 light bulbs in series, so that means we have 3 resistors in series. And in fact, these light bulbs are, one is 100 watt, one is a 60 watt, and I think the other one is a 40 watt. Oh, sorry, can't answer yet. What? Okay, I had that question out of order. I'll have to remember to come back to it. So which statement is true about the bulbs? And of course, it is connected to a power supply. I'm going to connect it to an AC. That's the symbol for an AC. All right, we got 10 people have connected now. That makes me feel good. 7 of them have even answered. I don't know who. I'm not looking at anyone because I don't know who's answered. And it says, look in my eyes. I've done it. All right, we got 8 answers. 9 answers. Oh, yeah, we're getting there. All 10. Thank you very much. Kind of makes me feel, like I'm meeting my job requirement in some ways when everybody's answering. So here's our breakdown. We didn't have complete agreement. 8 people said they will have the same current. 2 people said none of the above. If they're in series, the thing that makes them in series is that current has no choice. It has no direction it can go other than from one into the next. So they have to have the same current. That is definitional for series. So now I have them set up right now in parallel because I was testing to make sure things would work. I have the power turned off because, this is 110 voltage. Actually, I'm just going to turn it on first before I rewire them, just so you can see. Uh-oh. They were all working before class. There we go. And here's normal power. So that's the 3 bulbs. Which one's the 100 watt, you suppose? How do you know that? It's brighter. It's putting off more light. Okay, now I am lowering the power, not because I'm worried about shocking myself and dying, but just because it's really bright. You can still see it. Turn it off, and I'm going to arrange these now in series. So when you connect things in series, what do? You go in one side, out the other, straight to the next one. Out that one, straight to the next one. Not that it matters for these, but I'm going red to black in each one. And then I need to go back to the beginning part. Now, we physicists, we're just crazy cowboys here. I've got 120 volts, well, I lowered it a little bit, and it's just all connected here. There's the 2 wires coming out of the wall right there. If you touch that, bad times.
Okay, don't touch it.
I won't. Right. That's my plan. So here I have the 3 in series, and we're just going to see. Now, we don't have a meter here, so I can't tell you the voltage and current, but we're going to look at the brightness and see how it varies. I'm going to turn it up because this is not very bright. You can just barely see that filament, right? That's the opposite order of brightness, isn't it? So let's examine that before we go on. First of all, these light bulbs were 100 watts, 60 watts, and 40 watts. How do you suppose that relates to the resistance? What is the equation we learned for power? Power is VI. I heard somebody say that. And so since we're using resistors, I can use Ohm's law. We said all of them should have the same current. So I'm going to replace V with Ohm's law. So V is equal to IR. So that's a way of calculating the power. They're all going to have the same I squared. The one with the biggest resistance is then going to have the biggest power consumption. The one with the smallest resistance will have the smallest power consumption when they're in series. But these light bulbs were rated for 120 volts. So I could have also rewritten Ohm's law using voltage as equal to I is V over R, V squared over R. So for the rating is 100 watts is equal to 120 volts quantity squared over R, which means R is equal to 120 squared, that's 1400, divided by 100. That's pretty easy math. The resistance of this is 144 ohms. This one here, 14400 divided by 60, that's a little bit hard. I'm actually putting in a calculator. Is 240 ohms. And the 40 watt is 360 ohms. And of course, I should have been able to do these in my head, but I didn't. So now we can look at this and say, okay, they all have the same current, but the one that's rated as 40 watts has over twice the resistance. And since it's for same current I squared R, it's over twice the power in this one compared to that one. So that all makes some sense. Now, another woo clap question. For these three light bulbs in series, what happens if I unscrew one of the bulbs? Yeah, one woo clap. We're at 6, 7, 8. Nine. One more. Oh, this is very applicable to Christmas lights. You have Christmas lights that come in different wiring arrangements. And if you're acquainted with the 12 pains of Christmas.
Christmas
Oh my
lights.
goodness, have you heard that song?
Oh, yeah.
It's so funny.
I'm going to quote it here in a minute. All right. Last person going to answer? I got 5 seconds and I'm going on. Okay, well, the answers we got were 4 said only that bulb goes out, the rest stay the same. 2 said only that bulb goes out, the rest get brighter. And 3 said when one goes out, they all go out. Because that's the quote from the song. So, of course, we're in physics class. We do this to see if that's right.
Yes.
One goes out, they all go out. Now, let's answer why, right? Just getting an answer isn't all that fulfilling. Andy.
The circuit's not close anymore.
The circuit's not closed anymore. You don't have a complete loop. Hence, you have no current. Now, I'm going to turn this off before I do something silly. Screw this back in. Just which one was it?
This is gonna be the only chapter in this whole class that I understand.
All right. So now I'm going to change over from series arrangement to parallel arrangement. So here's the question you're going to have. Once again, this is wonderful. Well, what I'm going to do, because obviously I forgot to put these in.
Wait, no, this one was.
I'm going to come back to this. It's this question here, except for changing series to parallel. That's the next question. And of course, on WooClap, it'll show you the question correctly. So I'm rearranging, answer the question, what would happen if we change to parallel, and then we disconnect. Well, actually, the first question is, what's the relationship that's true? So to put them in parallel, I'm going to put red wires going from red to red. Red to red. Blue wires on the backside. And then connect these up to power. Red goes here. Blue goes here. Make sure they're not touching. All right, let's see how we did for answers. We have 3 answers. 3. I open it up again so you can continue to answer for the majority who didn't answer. So we're changing this question. Instead of being series, we're now asking for if it's parallel. Up to 6, 7, 8. That's everyone but Max and one other. So what we have now is we had 5 people that said, that said for parallel, and 3 people that said none of the above for parallel. So if they're in parallel, and of course, I'll draw the parallel arrangement here. The definition of parallel is the tops are all connected, the bottoms are all connected. So that means that the energy difference going from the top to the bottom is the same for all of them. What do we call that energy difference per charge? The voltage. So it has to be that the voltage is the same for all of them. So the answer here was they have the same voltage, the one that 5 people answered. But then we have the follow-up question. So if they're in parallel, so you can answer this starting now. If they're in parallel, what happens when I take one bulb out? We have 5 answers, half done. 7 answers. 8 answers. That is all we're likely to get. Oh, we got 9. Everyone but Max. Nice. So for the parallel, we had 5, 2, 2, 0. So we didn't have quite as much, we didn't have good agreement on this either time. So, of course, now we do the experiment, right? We turn on the power. They all light up. Lower the voltage a little so it's not so bright. And I'm going to unscrew the one that's dimmest because you know what that means? It's not as hot. So, let's just see what happens. One goes out. What happened to the others? They what?
Oh, they should get brighter. It's the same voltage.
Do you see them varying?
They're the same.
They're the same. So the correct answer here for parallel was the rest stay the same, but that one goes out. So why?
Because there's more than one pathway.
Okay, there's more than one pathway. The voltage across it, I put another one on, the voltage doesn't change. Take one off, the voltage doesn't change for the ones that remain. Because they were, well, that's part of being in parallel. So when it comes to Christmas lights, why would you put lights in series versus parallel? Think about reasons, because they come both ways. If you do it in which way? If you do it in series, you have to guess which one's out. If you do it in parallel, you know exactly which one's out.
But if you do it in series, you probably have to use less wire, so it's probably cheaper to manufacture.
Okay, if you do it in series, you're going to use less wire. That's definitely true. What we have for our Christmas lights that are still hanging outside our house because Amy loves Christmas lights is a bunch of sections that are in series. That is, this section is all in series with each other, but then there's a parallel, the next section. Why do you suppose they did that? Yeah, so you know, oh, I have a light out in this section, but then you have to go and check each stinking light in that section.
At least it's not every stinking light.
So
That's right. At least it's not every stinking light.
when you go by Christmas lights, do you like to look for
They usually don't even say.
okay.
This I probably could have figured out because it has 4 fuses inside of the plug, one for each of those circuits. So it has 4 different sections on it that are. Okay, so wanted to get this practical thing about series and parallel to close off circuits. Now our last question, which I had to skip over because I had it out of order. What is the purpose of a capacitor? Because the transient circuits, we're going to be dealing with capacitors here. And we're going to be able to see the practical usage of a capacitor for once. Well, I'm not going to do a demonstration, but we got one answer. Oh, now we got 3, 4, no. We have 2 answers because this one is answer all that are correct. Okay. I was counting the number of answers and not the number of people who had answered.
Oops, wait, I want more.
I want more. More. 8 answers, 9 answers. We are on a roll with this one. Okay, we'll get 10. 5 seconds to get that 10th answer. And no, we only got 9. Okay, well, the answers we had, 6 people said the capacitor's purpose is to store energy in the form of charge. 6 people also said capacitor's purpose is to store energy in the form of charge separation. And 4 people said to store energy in the form of electric field. 2 of these answers are fundamentally meaning the same thing, and one is different. The one that's different is A. A is not correct because you don't store charge on a capacitor. When you charge a capacitor, it certainly sounds from the vernacular like you're storing charge, but you don't. You store a charge separation. And so you have one plate will be positive charge, and one plate will be the negative charge.
Why is that not storing charge?
Because the net charge is 0.
Okay.
And so it's not storing charge because the total charge is 0.
So while each plate is storing a charge, the storing is in the form of
The capacitor is both plates, so the whole thing is
the whole thing
not.
doesn't have any charge.
Yeah. Now that's general physics explanation. You can do things to put charge on just one side, but we're not. So our answer was both of these. To store energy either in charge separation or electric field. The real key here is to store energy and then how we're doing it. Because in application, here is a simple application. Something like, let's say that you have a camera with a flash. Come over here because here I have a camera with a flash.
Old school.
Here's the flash mechanism. So how does this work? Well, it's actually reasonably complicated because it's got something that's going to take a battery, actually a single cell, because inside of this, they're all broken apart. Well, here's what's inside of it. What's this? A AAA cell. So it's powered by a AAA cell, and it has a capacitor and a circuit on that board that I showed you that is going to take the cell and create an alternating current first, and then it uses a transformer which allows you to raise the voltage really high, and then it goes back to DC. So it's a complicated circuit to give you a high voltage DC from a 1.5 volt cell. And so then that high voltage goes through a resistor to charge that capacitor. And so when you charge that capacitor, you're storing energy. And remember, the capacitor stores an energy of 1/2 CV squared. If it was only a 1.5 volt cell, you'd have to have an enormous capacitance. Capacitors, did we talk about the units of capacitance? I don't think we did. The units of capacitors, we call them farads. And if you do the calculation, you can find what it is. It's short for microfarad. Farad.
Ferrets, like the little
Like the animals? No.
And I was like,
And typical capacitances are on the order of 10 to the minus 6 farads. And so if I have 1/2 times 10 to the minus 6 times 1.5 squared, that's going to be something on the order of 10 to the minus 6 joules. You wouldn't get much energy. So you have to have a large voltage to get a large energy. So that's why it has the high voltage. Then it stores energy, and what's that energy used for? In the flash? It goes through a filament, just like these. These have a tungsten filament in there, a piece of wire that's very thin. And when the electricity goes through that wire, because it's very thin, it has a pretty high resistance. Remember, resistance is equal to the resistivity times the length divided by the area. So if area is small, that resistance goes up. Higher resistance means more energy is extracted when charge goes through. And so it's a pretty large resistance. It's going to extract a lot of energy when the charge goes through. And while 95% of that energy makes things hot, 5% of it comes out as visible light. And so we see that flash. So the whole point of the capacitor there is to transfer energy through the complicated circuit that we don't see from the cell to the capacitor, so it's storing a large amount of energy. Now, what is the cell storing? It's storing energy in the form of a chemical reaction, the voltaic cell, like battery cell. It's storing energy in the form of a chemical reaction. You have reactants, and those reactions can go and produce a certain amount of energy. So if you look at, for instance, my laptop battery went belly up on me. By belly up, I mean it went from this thick to this thick. Apple said, oh, that's fine. You're fine. Oh, don't use it for sure because it can start a fire, but you're fine. There's nothing wrong with that battery. Apple does not stand behind their products. They do not anymore. Anyway, so I had to replace it. And these batteries are rated in units of Amperes, hours. Well, what is an ampere? An amp.
That's a measure of current.
It's current in units of coulombs per second. It's how much charge per second it can supply. And then it has times hours. So that's the total amount of charge that it can supply through its chemical reaction is what it's telling you when it says ampere hours. Now there's also a voltage, and because power has to do with the voltage as well as the charge. And so it stores a lot of energy in chemical reaction that if it goes to completion would give you that many coulombs of charge in the end that it would give the voltage difference to. So it's storing a lot of energy in a chemical reaction, but that chemical reaction takes time for it to occur, which is why when you start to use a battery, the terminal voltage drops a little while you're using it because the chemical reaction takes time. So you have this capacitor, so you can, over time, transfer energy from the battery or the cell into the capacitor because the capacitor can dump its energy really quickly. Now, this brings up some other cool things like, why don't we just use capacitors for our cell phones? Because the cell phone is going to take a long time to charge, right? Like an hour. Whereas if I had what they call, I think they call it a supercapacitor, I could charge my cell phone in, mere seconds, as long as I have a Tesla charging station available to me because you get a lot of power in a short amount of time. So why don't we have ultracapacitors in these babies? Or supercapacitors? No, you can have energy density that's the same as a battery, pretty much. I don't know how expensive they are, but I don't think they're as expensive as lithium-ion batteries. What's the danger of the battery in your cell phone to begin with? It could explode. Say you had Samsung, what was it, 7?
It was like the Nexus 7 or something?
I think it's the Samsung Note 7.
Oh yeah, that's what it was.
They started, blowing up, catching on fire. You still can't fly with that model of phone if you still have one that's, alive. It's because when you use the batteries, they expand. And that expansion, if you don't have space, they did not design the phone with enough space for the batteries to expand. And so that compression caused them to fail. And once they fail, that energy can be released reasonably quickly. But if you had a supercapacitor, ultracapacitor, whatever it's called, it would release the energy pretty much in no time. So it would release it a lot quicker. So the danger would be much greater. So there's a good reason not to have those. Now, just to combat myths, they're humorous and funny, and yet you see them. You see the thing that says they're just trying to make your life hard. You can charge your phone in 5 seconds by putting it in the microwave.
Not a good idea.
People have done this because they saw it on YouTube, and who would lie on YouTube? Well, everybody lies on YouTube, right? You put this in the microwave, and you know what a microwave is? It's sending electromagnetic waves. Now, this uses electromagnetic waves to communicate. In fact, the microwave frequency is really close to the frequency you use in your 2.4 gigahertz Wi-Fi routers. It's electromagnetic waves. We haven't learned about those yet. That's going to come right before the next test. But you have electric fields that are oscillating. What happens to an electron if it's an electric field? The whole point of the electric field is it allows you to calculate a certain property.
I don't know what you're going for.
The electric field is defined as the electric force per charge. So if I have an electron-electric field, it's going to have a force on it to make it move. And if it's in a conductor, like the circuit board of this, the electrons are going to move in response to that microwave radiation. That's why you don't put metals in microwaves, because it'll just make electrons move back and forth with them, transferring a lot of energy into the metal and causing problems. So that's what happens to your phone too. It doesn't charge it, it just makes the circuit board catch fire and things like that. Also, other things, you cannot pop popcorn with your cell phone. You may or may not have seen those bogus videos on YouTube. They put out microwaves, absolutely. Nowhere near the power necessary to pop popcorn. Even when you have a whole group of friends put their phones around one kernel of popcorn, it doesn't pop. Okay, so back to this practical. The flash is storing energy on the capacitor. The capacitor can give it out really quickly. So when you're storing the energy, the resistor, of course, is going to limit how quickly charge goes. If you're going to have a large current if resistance is small, a small current if resistance is large. We learned that from Ohm's law. This capacitor, if it starts with zero charge, since V is equal to Q over C, if it starts with zero charge, what's the initial voltage on the capacitor? Zero. But as soon as you have current flowing, this top part becomes positive and the voltage rises, which means the voltage drop across this is decreasing. So phenomenologically, without actually doing calculus, you can understand that as soon as you start having current flow, the voltage on the capacitor starts to rise, which makes the voltage difference across the resistor smaller, which makes the current smaller. So the charging is going to be fastest initially and then slow down over time as you charge the capacitor because the capacitor is charging up. And so you get this equation or this graph for the voltage you're going to have in the capacitor as you charge it. The actual equation for this is real simple.
So that's the equation that you get from charging a capacitor.
Okay, I put this V0, that's the voltage it had when you started. V infinity is going to be the voltage you have after you leave it for an infinite amount of time. And then tau is the resistance in your circuit multiplied by the capacitance in your circuit. We call it the time constant or the RC time constant because the bigger tau is, the bigger R times C is, the slower it charges. The smaller tau is, the faster it charges. So in the case here, what was the initial voltage? If we started with it with no charge, what was the initial voltage? Sarah said zero. And so we had for this case, for this specific case, we had V initial was zero, and the V after infinite time is going to be the EMF of the battery. And so it's minus the EMF, e to the minus t over tau plus the EMF. What does EMF stand for? Electromotive force. A discredited term because they were thinking that batteries were putting a force on the charge. But actually, it's that chemical reaction that's going on. And so that's why it's a discredited name, and yes, to what we use. So that's charging. Here is a picture of if you discharge. So with that camera, when you press the button, a switch goes from the capacitor to connect to the lamp. And that lamp has a really small resistance. Small resistance means large current, right? So you have a large current that flows through that, and it will discharge with the same equation. For the discharge, V infinity was zero because you're shorting. As you can see here, there's no power supply there. V initial is, well, just V initial. And so this simplifies to this is going to discharge quicker because you're going to have a smaller resistance in that filament of the lamp. So this is a common practical use of capacitors. Store energy for something where you need a quick discharge. Another example, do any of you have a little, I hope not, a little taser in your pocket in case somebody attacks you?
No.
Always? No. I hope that people don't have to have that fear, but I also live in a world where people do have that fear for legitimate reasons. But if you're carrying a taser in your pocket, it's not charged with a big high voltage battery. It's charged with normal batteries. It's doing exactly the same thing as that flash circuit, except for it's storing more energy so you can dump it in a person and make them undergo seizures. Because remember, if you get more than about 10 milliamps going across a muscle, it'll cause the muscles to contract. But you want to get that amount of current out, and so you have to store a lot of energy in a capacitor so that you can dump it into a person if you're going to use a taser. Don't tase me, bro. It's one of our things we don't like. You've seen the video, right? Okay. Some guy's causing disturbance. And it's not important. Another practical example, a type of strobe light. With the filaments, like this light bulb here, we calculate the resistance in the bulbs, right? But those resistances are the resistances they're going to have when they're hot. When they're cold, they're going to have a different resistance. And with this tungsten, when it's hot, it has a lower resistance. Tighten this back up so next time I use this, I know it. Has lower resistance when it gets hot. So you create this simple circuit. There is nothing complicated in the circuit. You have that resistor, capital R, that's your charging resistance. That's so you aren't just connecting your battery to the capacitor and having the capacitor try to charge instantly and melting wires. So that's the point of R, just so it doesn't charge too quickly and have too much current. Then you connect it to the light bulb, and as the voltage on the capacitor rises, when it gets up high enough, you will have a current start flowing through that filament, and it gives off light, and the voltage drops, and it gives off light while the voltage drops until it gets to a low enough voltage and turns off. And so what happens is the current that is flowing through that light bulb is, during these times here, you're having a good sized flow. During the rest of the times, it's kind of a trickle. And so it's flashing each time you have that burst of current flowing through the filament. And so it's making a strobe light. Is that cool? In practical design, when you're making an oscillator, you use capacitors as part of your circuit for an oscillator to make something that's going to oscillate, like a radio transmitter. Because of this energy storage capacity. Yes?
So if you're using a capacitive circuit, is the point to like bring energy up and down?
Well, the point of the capacitor is to store energy.
Okay.
The point of the circuit can vary.
Okay.
And so in this example, we had the filament has certain properties that combined with that capacitor will make it oscillate. And so somebody said, hey, we can just combine these and get an oscillator without any complicated circuitry. Last thing before we start on magnets, and we will not get far with magnets today. Why is it not safe to touch the wiring inside of an electronic device right after you turn it off? They have capacitors. They're still storing their high voltage. You know, crazy example, I used to have a nice 65-inch projection TV. Of course, projection TV, it's just got a little, you don't ever want to mess with tube television, just to be clear. The tube televisions have like 10,000 volts that they use to accelerate an electron, give that electron the high kinetic energy. And how do they get that? Well, they go through a transformer, store on a capacitor, and then that capacitor is connected to the electron gun, as we call it. So you have 10,000 volts. You unplug it from the wall, you still have 10,000 volts on that capacitor. And so if somebody just unplugs the television, takes it apart and reaches their hand in there, they could very well be electrocuted. And remember, electrocuted doesn't mean shocked. Electrocuted means executed with electricity. That's a bad thing, right? So don't be tempted to work on a tube television. If you are, make sure you've unplugged it for a while. Open it up, and they usually have a place that says insert ground here, and you should have a ground rod somewhere that you plug in there, and that will drain the capacitor so you don't die. So bottom line is, without training, it's just really bad form to work on a tube television because of those high voltages. I had students, for one of their projects, they used the voltages produced by a television to make a little levitating thing. It was actually really cool, but scared the dickens out of me because you've got this thing floating around with 10,000 volts. And, that doesn't seem safe. All right.
Is that when they're expensive to dispose?
No, it's chemicals. All right, magnetism. Picture here is awesome. What do we have on the right-hand picture? Okay, Aurora Borealis / Northern Lights. What does Aurora Borealis mean?
The Northern Lights.
Yes, it very literally means the Northern Lights. Borealis is northern, Aurora is those lights. So we also have Aurora Australis. Because what does Australis mean? Southern. So you have southern lights and northern lights. What causes them? It has to do with the Earth's magnetic field. Now, the Earth's magnetic field does not cause them. It has to do with it. The Earth makes a magnetic field like it has a bar magnet in it. So we will, when we come back on Monday, talk about bar magnets and magnetism and how a compass works and so on. But the Earth behaves like it has a bar magnet, and when charged particles from the sun, because the sun is constantly emitting what we call a solar wind, there are particles coming out of the sun constantly, and they hit the Earth. And charged particles are going to have a force due to the Earth's magnetic field. Not magnetic field, magnetic field. It's a different thing. And that force deflects particles, so if they're coming close to the equator, they just go out. It splits them like you have some kind of guard up there, some kind of shield. But if they come close to the poles, because those magnetic field lines curve into the Earth, the charged particles will actually spiral around those lines and come on in. So you're going to get a lot more of the dangerous kind of radiation that comes from the sun if you're in northern or southern regions than if you're in equatorial regions. And the northern lights, the southern lights, are caused by those charged particles coming through the atmosphere. I'm going to cut it off right there. It's a great place to stop. And we'll have a lot of fun next week talking about magnetism. Well, and then we'll have tests on Tuesday, but otherwise we'll have a lot of fun. Actually, we'll talk about magnetism on Monday, or are we reviewing? I should look.
Can you help us with this one problem?
Yes, I will do the math more carefully.
So I did it and I got a different thing than you did. It's a little bit different, but it's still not right.
Okay,
I'm tired of doing this problem.
have a great vacation, everyone, and I'm going to help these ladies with that problem. Okay, so I'm going to bring paper and do it carefully this time.
So the area that I saw was like, you suddenly changed yours, you had like a hard to come out of nowhere.
Okay,
So then I changed it to just be something. Yeah, it's just to do the whole time. I don't know.
let me start with the 3D. Let me just get this straight. So the circuit has, this is I1, right? I1.
These equations are correct. I1 equals I2 plus I3.
So I'll start this. So equation 1.
Next.
I1.
You okay? Are you okay? Can you go to the doctor?
I'm gonna go up to class.
We got it.
Where is it as well? Oh, that's not even the right paper.
It is. I can do
It
this.
is sorry, the right paper. Just wouldn't you have the same problem as if you went to school in the Caribbean? You had
I don't think it's this. I don't think it's this guy.
You're on to go to
Um,
Canada?
That's fine.
Why not?
Okay, so this equation here is the correct one, not this one. Sorry. These are different.
Yeah, these are the correct.
Okay, so which one's this? Okay, actually, I should just.
Here, you can look at my actual thing.
It's
if you
this
want.
sort of thing.
Like, those are the answers and I got them correct. I don't have.
Very right. Yeah, okay. No, it's okay.
I'm thinking about trying to get into early admissions for.
Oh.
Because I just want to do student missionary work anyways, then just look and pay off my debt. So that I could go to missionary work as soon as I'm in school, or residency. So.
Do you see your attention a line, like 2 lines to the 15? Could you just do like one round?
Theoretically, that sounds okay. Is that enough attention though?
In the greater one, yes, if you're not doing like a highlight. So if it's just to keep it.
Then I think it would work.
Why would you do it?
I don't know.
Well, and then you can run, you do this, and you can.
For next Friday's third. You mean next Friday's third?
No. When, no,
Oh,
so, listen.
so we still have like 3 weeks of school left before, once we get back.
They get back to the 11th.
Okay, so like a whole month almost.
11 forced students enrolled in Canadian institutions.
Dude, Anna, let's like,
Is that like getting in or applications?
11 medical school, 11 US citizens, 11 people outside of Canada.
I wonder if that's because the ratio of like people applying was so low, or if it was just because they don't accept.
Maybe you're not in Canada. You're in charge. And 3 of the schools are only in French. Oh,
Perfect.
I can't learn any language.
But aren't you Canadian citizen?
I could be. I think I can have dual.
Yeah, I'm not.
what's on there?
It's like getting a green card here.
What? No.
I'm married, so I can get a green card.
No, so I can go to the games. I can go to Calgary and
So far, that looks like the same thing I ended up getting.
I don't think I can. I think I'm not becoming a US citizen. But I think I can be a dual next year. So that's.
The last one's the easiest way to write it. Is that different from one of the people?
Yeah, for sure.
Okay, I'm just.
You didn't have to put
gonna
R squared. It's because you randomly put an R2 in there that wasn't in there.
Okay.
So
But-
anyone,
I think that's the same thing that I have, and it's not.
E1, negative E2.
Why do you have negative E2 R1?
Yeah.
There's no way. There shouldn't be an R1 with that.
I'll try. Yeah, I had to put I'll try.
I've tried it so many times.
Just looking at how I got there,
Still.
I had B2 by itself, right?
Yeah.
So I had E2 by itself here, and then I multiplied top and bottom by R1, such that this R1, as well as this R1. And this R1 disappeared, that R1 disappeared. So these two here are exactly the same. Either one of these to be correct. It's just that one's supposed to be correct.
Hey, it's right.
I think I did do that right then.
That's the feeling I had.
It's that one. Wait, let's just put it in now.
She
Wait.
already did.
Yeah,
Yeah, I was like, I don't even care.
Deuces.
I have a.
But what you see is this is why I showed you how to use RREF.
Yeah,
this section was
thanks.
super obnoxious. R2.
Do we have a, we'll probably have one more.
What was it?
How did you put it in, Olivia? Can you see how you put it in?
Do it
Yes,
this one.
ma'am.
Just do
I
like
put parentheses around each side. Parentheses.
So
divided by
parentheses here and then parentheses here.
Mr. Chapman.
No, don't fall.
Ask me.
I must have misunderstood something because that's not what I answered first.
And
R3,
when we get out of the
R2.
pool, I'm literally booking.
Pull up the chair and swell and stir.
Where are you going?
Oh,
Oh, really?
Yeah, I think that's what Karen and I
it's a
do.
busy looking
Which I feel bad because I realized that
Where are
we're.
you
No,
going?
it's
I gotta
not.
go to the stage right.
So I've got
Really?
two
Why?
numbers,
You were not.
two meshes, three equations. And my equation is obviously.
They don't look in
R1,
here.
R2, E2, R1. R2,
So what's your
R1,
question?
R3, R2, R3, R1.
I1 out.
Oh, wait, I did
Two,
wrong.
so it's negative.
One, R2, minus.
Okay, perfect. And that'll zero, that's right.
R2, R1 plus R3, R2 plus R3,
Okay, so
R1.
let's take the top mesh.
So
So I'm gonna start,
You do two.
I'm gonna start at A at the top.
You have an extra one there. You have an extra parentheses.
I1 R
Hi, I love you. Have a good break.
plus E1 minus.
Love you, Leah. I'll see you at
And lifeguarding partner, yeah.
Let's go.
Let's go.
R5. And then I get from here, now it's going to the
Problem
right,
so
so I'm gonna be going
Let me
back.
tell you.
So plus I2 R2 plus I2 lowercase r2. Then I'm going to plus C2.
So I just focused on I1 and not bother with I2 here.
Well, I2 is going through this. So
Right.
that was going to depend on I1 is this. That was
Yeah, no, for ID exam, no way. But like even learning like the FA stuff. Gotcha. I'm gonna go to Carrie's house so that I can like not be here, but.
So then.
Bye.
You too.
It's gonna be times of
I was like,
minus
I'm gonna be studying for my school.
Yes, that's
Okay.
25.1.
Yeah, I like her. I don't really know her that very well.
That's pretty cool.
Plus E1, which is
plus.
I2. Why is that positive?
Do you want that?
Because the current.
I didn't do that.
But the current was going to the right.
Yeah.
We were going to the right.
I appreciate you.
My math is right. You just wrote it a different way. My second one, not my first one, but my second one was right.
Now we're going against the current.
But I thought this is I2.
I just don't know why I didn't, like when I plugged it in, I didn't get the right answer.
Yeah, we're going against the current. We're going down.
You should be so proud of me.
Yeah, we can't reverse it.
No, I missed OChem all day. Triple A is fun.
So then I do
I got
I2
like all my stuff done, and I
times
already finished the South London work on accident. I was like,
That's pretty good. I'm proud of you.
and then that's going to be plus.
Now, are you ready for our coming today?
Because we're going to.
Yeah. I mean, we just sit there and do it, so.
So-
Yeah, it's actually really easy. So be good.
Okay, so this is a cycle, and to get I1, I follow this cycle from E here. And then from I2, I go here, go from here to there, but I multiply everything by I2.
I mean, you're just applying Ohm's law to each resistor.
Right.
Remember, the way I told you to do it is to draw arrows above each resistor and then mark which side's the plus and minus. And then as you go around the circle, you just, if you went from plus to minus, then it was a drop. If you went minus plus the price.
Okay.
Okay, so there's that equation.
So there's that equation. So then this lower equation here, I'm just going to use I3 here, and then everything else is I2.
No. I3 goes from here to here.
Okay.
So to make it easier, the way you're thinking about this, we'll start here. So you're going with I3, so that's negatives.
Right. Plus I2.
So
So
I2, you're
I2
going with it, so that's negative as well.
negative as well. So this is going from negative to positive, so that's a positive. So that's positive E2, so that's 41. Plus I2, we are going with it, so it's positive once again. No, negative.
Right.
So I2 times negative 40.5 plus I3, and we're going with it, so it's negative again, so that's 78.25. And then minus, well, that one's minus.
Right, one's minus, one's plus.
So that's E4, which is 36, plus E3, which is 14. Zero.
Okay, those are all correct.
Okay. So
And
now,
then you put them in your calculator.
right, I need to rewrite things here. So 41 minus 28 is 13.
Okay. You leave it like it is, so when you come back, like, let's say you have a question preparing for the test. what's-
No, this equals 13 because I have negative 41, so I added it to the other side. This is positive 28, so I'm subtracting from the other side.
Okay.
That was a good one.
Okay, I don't wanna work the problem. I was just, wanted to leave the equations in the way you originally started them, so when you come back and review, you can see where you got those numbers.
It's like seems like the
I understand.
this was 41 equals 0. See, that just irks me. Okay. Because now I have to do math and say this is 13, because I got to make it a matrix anyway. And so I basically have my fourth column as everything on this side of the side.
Yeah.
So if they're already over here, then I get confused. That's why.
Okay, and so, you do the problem the way you like. I just didn't want you to make it so we can't come back and be confused. But if you're confused now, that didn't help, right?
Right. So negative 41 plus 36 minus 14. So that's negative 19. Okay. Matrix, edit, 3 by 4. Okay, negative 1, 1, 0. Negative 25.1, 40.5, 0, and 13. I've got 0, negative 40.5, negative 78.25, and negative 15.
If that one's right, the other's probably right.
Right. 2, 4, 3, 0. And 7, 1. And was this the one they were really confused on?
It's not that it's confusing,
Mhm.
it's that it forces you to do it by hand instead of using a calculator.
Okay.
That's the frustrations. Right, now that you know how to do it on the calculator, that was quick, right? You got the equations and boom.
Yeah.
Not so much.
So for here, I basically do it all by hand, or I do the whole substitution.
Yeah, and this leads you through the solution, so you find each equation, equation 1, equation 2, equation 3, and then it tells you to combine them to find an equation for I3.
Okay, so once again, 3 equations. And let's go with E here. So I1 is going out, so that's negative in plus I3, which is going in. Then let's do this top loop and let's start from E here.
Well, oh yeah, due to the low probability of deployment, the first question is the equation you just made.
This is that.
Well, read it. It says
Express the current I1 going through resistor I1 in terms of current I2 and I3 going through resistors R2 and R3. Use the direction of currents. But I haven't done anything with the resistors, so this can't be it.
That is a relationship between I1 and I2 and I3.
So basically the answer
The going through resistors is to clarify which one's I1.
I1 plus I2 plus I3.
No. That would be if it was equal to 0.
Oh, and I'm
That's
making it
I1
equal, so it's
just get rid of everything on that side. Yeah. Now write equation of potential charge in loop EBAF. So it tells you
EBAF. Okay. So that's going from negative to positive. So that's plus 12. I'm just
using symbols.
okay. So E1 plus I1. Let's see, this is going out, so it's negative. So this is going to be negative. So R1 is going to be negative. So I1 times negative R1 plus I3, which is going in, times positive R3 is going to be equal to 0. No?
You were going with I. Right here you were going.
Oh, that's right. I'm going with it, so it's negative. So if I'm going with it, it's negative. But if I'm going against it, it's positive. Okay, so then I go E1 minus I1 R1 minus I3 R3.
Wow.
Okay, so loop DCAF, so all the way around. So I'm going this way, and these are flowing against the current. So we're going to, this is going from positive to negative, so that's negative E2 plus I2 times R2 plus I3 times negative R3. So negative 2 actually, that's what it's, I'm going to start with I2 R2 minus I3 R3 minus E2.
Now you have to combine those.
I3.
So combine the top two to eliminate I1, and then combine that new equation with the bottom to eliminate I2. So basically take the top equation, solve for I1, plug that into I2.
Okay.
Then solve this new equation for I2, plug it into the
So I2 is I3.
Well, no, top of the top.
Okay. So this one's already solved for I1, so I just plug that in down there. So 1 minus I2 plus I3 R1 minus I3 R3 0. So now I'm looking for I3.
So first you solve this for I2. So
Yeah.
substitute that at the bottom. So
So I'm going to get negative I2 1 plus I3 1 plus I3 3, and then I2 is going to equal E1 plus I3 1 plus I3 3 over 1.
Okay, so to that, I'll do the final equation.
Which is going to be this one. So then this is going to be 1 minus 5 plus times R1. Oh, yeah, no, R2. This R3 minus 0. Now solve for R3, I3, which now this is getting complicated.
At this point, your easiest move is to multiply everything by R1.
All right.
You got this.
Yep.
I forgot my lunch, my wife's lunch, so I need to run home. So lunch return.
That is important.
It is. You know what else is important? To not leave this out where somebody could come play with it and electrocute themselves.
That would be bad.
Because you know this is not safe.
No. Have a good break, guys. I'll see you.
Thank you.
Yep. See you. All right. So anything with no I3 goes out. So, negative 3, 3. All right, factor out I3. I will negative 2 minus 3. 2 minus 4. Okay, so holy cow, this is a ridiculous equation.
That's what the girls were upset about.
Negative E1.
Call you boy, but I can't call a woman a girl.
Yes.
Somehow I still have in my head that girls are females and boys are males, and that's the end of it. But I've got to improve.
What? That's not right. You have a sign. Here's a numerator of other terms. Oh, negative divided by